Today we're going to talk about, I'm going to show you something for your math class. It will be related to things we'll do in this class, but it's not related to things we're doing today or things we've done before, but it's something that can help you for your math exam tonight, perhaps. I'm going to talk about tension, a little review, and then I'm going to talk about bending, which is what you've been doing in the lab this week. Okay, so to start with, let's just talk about dot product. And the reason I'm showing you this is I just overheard people wondering about these simple trig identities. And so here's a little trick for remembering the trig identities in case they don't give them to you on exams tonight. And it's worth knowing this trick for future reference. So if we have two vectors, say A and B, and we have the angle between them, which I'll measure like this as theta, there's this formula for the dot product, so-called dot product, between these two vectors. And the dot product is an operation between the vectors which gives a scalar. And the meaning of that scalar is the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. And that's the geometric definition of the dot product. Sometimes people write this thing, the magnitude of A is just A, and they write this as just B, and it's AB cosine theta. Who does not know that formula? Now, who has not seen that formula? Okay, so it means you haven't taken physics somehow or other, right? I think is what this means. Has anybody taken physics and not seen that formula? So how could that be? Okay, so this is you definitely want to make friends with this formula. There's no question about your need to make friends with this formula and understand this concept. Now, each of these vectors, A, if you have this vector A, which looks like this, you can break it up into components, which are the projections. Here's the word projection, which some people had trouble with earlier in this course, which are projections in this in these directions, AX and AY. And if on the side here we have a coordinate system with unit vectors lined up with I and J, we can say that the vector A is equal to AXI plus AYJ. It's the sum of two vectors pointing in the two appropriate directions. So this dot product formula, it turns out, has another representation, which is AXBX plus AYBY. Because the vector V, similarly, is the sum of two vectors parallel to the x and y axis. Now, why this is true? Well, it turns out to show that this is true, you have to use what I'm going to tell you. So it's very much circular reasoning. But the fact of the matter is that it's easier to remember this and this than it is to remember the cosine, the formulas for the cosine between two cosine of theta 1 minus theta 2. Okay, so you have to, I would guess, say memorize. I hate the word memorize. It should be know this. You don't memorize the name of your friends. You just know them. You don't memorize your home phone number. You just know it. These are things that you should just know. It shouldn't be like random facts that are disassociated. Okay, so you have to know this. Given that you know this, how can we get this these cosine formula, the cosine difference formulas? Is what you do is you draw a unit circle. That's one of the best circles I've ever drawn. Very good circle. And we take two unit vectors. So this is a unit circle. It's got magnitude of 1. And we look at two vectors here, B and A, both of which are unit vectors. And they make angles of theta 2 and theta 1 with the x-axis. And between the two is this angle theta. So theta is equal to theta 2 minus theta 1. And here we'll call this the vector B, and we'll call this the vector A. So what we'd like to do is just equate these two different formulas for the dot product for those two unit vectors. Okay, so B is equal to cosine theta 2 I plus sine of theta 2 j. A is equal to cosine of theta 1 I plus sine of theta 1 j. So these two together give us that A dot B is equal to cosine theta 2 cosine theta 1 plus sine theta 2 sine of theta 1. On the other hand, we know that A dot B is also equal to cosine of theta 2 minus theta 1, which gives us this identity that cosine of theta 2 minus theta 1 is equal to cos theta 2 cos theta 1 plus sine theta 2 sine theta 1. And if you don't like it this way, you want to put cosine of theta 2 plus theta 1. You substitute in minus theta 1 in this formula. The cosines don't change because cosine of a plus angle is cosine of the minus. The sines do. So it turns into cosine theta 2 cosine theta 1 minus sine theta 2 sine theta 1. But this is the one that's sort of most fundamental in terms of this derivation. Where do the i's and j's come from? I and j are unit vectors parallel to the x and y axis. So this goes along with the x and y axis, and it's saying that this vector A is a sum of two vectors. One vector, which is axi, and another vector, which is ayj. Another question? So what's the key to this is knowing these two different ways of thinking about the dot product, and then taking the dot product of two unit vectors and thinking of that dot product both ways, both in terms of the components of the unit vector and in terms of the angle between them, multiplied by the magnitudes of the vectors, which are 1 and 1. Once you've seen that, you don't have to write it all down. You can just remember, you can just do it in your head, and you know that cosine of theta 2 minus theta 1 is cos, cos, cos minus sine, sine. Sorry, plus sine, sine. Questions about that? Who's seen this derivation before? Raise your hands. Who has not? Of those who have not, who understands what I just did? Who has a question about what I just did? Who doesn't have a question because you're so lost you don't have a question? Go ahead, you have a question, please.
It was an actual question.
What?
Raise my hand up. Does it work as both sine or only cosine?
Okay, I'm not going to go through it so slowly with the signs, but I'll do it with signs also. Let's take those two vectors, A and B, and look at the cross product of these two vectors. The cross product of the two vectors is the magnitude of A times the magnitude of B times the sine of the angle between them. And this is not really right. It's a three-dimensional thing pointing in the k direction, but all I'm going to do is pay attention to the magnitude of it. Another way of looking at the cross product of two vectors is as this component formula, which is axby minus aybx, and this is also pointed in the k direction. And then we equate these two different formulas, and that means this expression equals this expression, but these are both unit vectors, and these are then the same cosines and sines we had before. So this tells us that sine of theta 2 minus theta 1, this is the thing we had called theta, is equal to what we get from the components, but all of these components are just cosines and sines of theta 2 and theta 1. So this is equal to cosine of theta 1 sine of theta 2 minus sine of theta 2 theta 1. A corresponds to 1, B corresponds to 2, cosine corresponds to x, sine corresponds to y. cosine of the first vector, sine of the second, and then we have sine of the first vector, cosine of the second. So if you know how cross products work, you get the sine formula as well. Does that address your question?
Yes.
Any other questions? So if you're not comfortable with dot products and cross product, this will not help you between now and tonight. It's too much to try to learn while you're trying to learn the other calculus things. But if you are, you can just learn it here and now, and then you don't have to worry about whether they give you the formulas in the exam tonight. Yes?
How did we go from cosine theta to sine theta 1 plus sine theta 2 sine theta 1 cosine theta?
How did we get from here to here?
No, from the top part to no, up higher. Where it says A dot D equals.
How do we get from
How did we
here?
get to there?
Okay. This difference between these two angles is the angle between these two vectors. And in the definition of dot product, it's the magnitude of the one, magnitude of the other, times the angle, cosine of the angle between the two vectors. Does that address your question? Let me start here. The definition of dot product is the product of the magnitudes times the cosine of the angle between the vectors. The cosine of the angle between the vectors is the difference between the angle each of them makes with the plus x-axis. Does that address your question? Any other questions about this? Ready for me to move on? I've been using an unregistered copy of something or other. Start session. Okay, are you here? Okay, I got a question for you. A, you have a laptop that you own that has MATLAB on it. A, you have a laptop you own that does not have MATLAB on it. C, you don't have a laptop of your own. Laptop with MATLAB, laptop, you don't have a laptop. You've got some other kind of computer. Or you don't have a computer. That's interesting. That's different than 5 years ago. Yes? Is there a what? MATLAB definitely works for Macs. I've got a Mac here with MATLAB on it. That's all you've seen. You can get it at the campus store. What? I didn't hear the whole question. Can you get what? Say it louder. I don't. You're not speaking over a college-aged language. You used a word I do not know that doesn't compute up here. Something or other illegal, something or other, plus something. I have no idea, but I did a survey the other day of graduate students, and the vast majority have illegal copies of MATLAB on their computers, which I can't support, but I can't argue with it either, really. There's a free software called Octave, which it will function for you just for most purposes as well as MATLAB. O-C-T-A-V-E. Okay. Happy to move on? You registered here? Okay, so we had this demo in class last time where we talked about a popsicle stick like this that we pull with some tension at the two ends. This popsicle stick has some length. It has some, I'll call this height, and I'll call this width. And the question is, can we figure out the change in length how much this gets longer compared to what it was before we pulled on it. So it got longer by this dimension, I'll call it delta L. What is this delta L as a function of the length, the width, the height, the tension, and the properties of the object? And we cooked up a formula which you all seem content with. Does anybody have any questions about what we did last class? Okay, take out a piece of paper. Yes?
What exactly is Young's modulus?
What do you mean, what exactly is Young's modulus?
What is it? I know it's like how would you define it?
That was the whole purpose of the class last time. So let me, I'll answer that question. We define Young's modulus for a linear elastic material as the ratio of the stress to the strain in that material, where the stress is defined as the force per unit area in the material, and the strain is defined as the change in length divided by the length in the material.
What I was meaning to ask is, like, if you were to talk like in English, not like in physical terms, like can you define Young's modulus? I got the physics part, but like.
Well, I think I spent the whole lecture doing that last time, but without repeating the whole lecture, are there any detailed questions? And I will get to that in a minute. But I attempted to do that last lecture.
What is the denominator for stress?
A. Okay, so take out a piece of paper, write your name on the piece of paper, and write down the correct formula that goes here. Write the name and the date, write down the correct formula here. You do not consult with your neighbor. This is what we call pop quiz. Notwithstanding that he asked a question which would totally answer this question, I don't want to do that. But I would like to see whether the rest of you who didn't ask any questions did absorb last lecture or not.
Just want the formula?
I just want the formula. Now, last class, some of you looked over my shoulder at the answer, which was on the screen of the. So I'd like you to not imitate that style and not look over your neighbor's shoulders. Who sees the remote control for the projector anyplace? Ah, it's in disguise. Everybody vote E. Oh, I'll just flush it. Never mind, you don't have to do that. A, when you're done. And done means you've done it or you give up. Yes?
We don't have to show really how we got to it.
Nope, I just want to know if you were with me last class or not. Just in sort of a deeper philosophical way. We're not having exams in this class, but part of why you're in school is to learn things. Part of what I'm trying to do is teach you things, and I would like you to be in the habit of actually trying to absorb things. I think some of you will easily be in a frame of mind. Sounds like it makes sense. I could learn this later if I wanted to, and I want to try and break you of that particular habit, and I'm doing it by this mean thing of giving you a pop quiz now. Okay, so write the date on the top, pass it to the end of the row, pass it in. Okay, so now I'm going to give you the answer. Most of you got it, but I just want to not only do I want to teach you the moral lesson that you should pay attention here and now, I also want you to learn things here and now. So I just want to refresh it in case you haven't got it. We assume often in engineering and science that when you make small changes, you get small effects, and that if you double the small change, you get double the output. You assume linearity. You do something, you do twice as much, you get twice as much out. So the assumption of linearity is a good one, oftentimes for many engineering materials, and that tells us that the change in length has to be proportional to the tension. So this one comes from linearity. On the other hand, if we take two things like this and glue them end to end, we get a delta L from one of them and a delta L from the other if we have just one tension on the end. So when you double the length, you double the change in length. And if you triple it, you triple the change of length. And that tells us that the change in length is going to be proportional to the length. On the other hand, so this comes from series, thinking about springs in series. On the other hand, if you take two and you put them side by side, then each of them only carries a tension of T over 2 if the total tension is going to be T. And if with the assumption of linearity, that means each of them is going to stretch half as much. And so the whole thing, which is twice as wide, stretches half as much when you have it twice as wide. And that's also true when you have it twice as high in these dimensions. And this comes from what's called thinking about things in parallel. This is called parallel, and this is called series. On the other hand, if you have one material or another material, they're not all the same. And if the material is somehow intrinsically stiffer, it's more like steel and less like jello, you'll get less deformation. So we get this other thing, which is a material constant. People in the class last time who cooked up a formula called this K, but it's not the spring constant K, because the spring constant K in this formula, if we want to say that the tension is equal to K times the change in length, the spring constant K, thinking of this thing as a spring, is equal to this modulus times the area, which is the width times the height, that's the area, cross-sectional area, divided by the length. So this is what we would call the spring constant. So it's not right to use the same letter for that. Instead, we have this material constant, which is the so-called Young's modulus. It's the stiffness of the material rather than the stiffness of the object. The stiffness of the object depends on the length, the width, the height. Now, what is that material stiffness? It's something that's about the material, not about the structure. So we want something that distinguishes wood from steel, not a wide beam from a narrow beam. So we have all these proportionalities having to do with the width, the height, and the length, and we want something that says that the steel intrinsically is somehow stiffer than jello. And what is it? We have to say, well, it's something which we scaled out the length and the width effects, and that's this ratio of stress to strain. So it's the ratio of the force per unit area to the change in unit length per unit length, change in length per unit length. Okay. So that's how come we can write this thing. We can invert this E, and we say the E is equal to the tension divided by the width times the height. All of this divided by the change in length per unit length. That's just an inversion of that formula over there. And this turns into what we call the ratio of stress to strain. Just so you learn the Greek alphabet while we're doing this class, this one is called sigma, and that's the word stress. And this one is called epsilon, and epsilon is the strain. And stress and strain seem like similar words, but they're actually quite different words. Stress has to do with force, and strain has to do with geometry. Strain is about deformation, stress is about loading. And this is somehow this intrinsic loading, the material loading. Okay. Now, any questions about Does this answer your question about what is it in English, what is it in math? Any questions about this whole formula?
So like Young's modulus is a property of the material irrespective of its dimensions.
That's correct. Young's modulus is a property of the material irrespective of its dimensions.
It's like resistivity in terms of electricity, like similar.
It's exactly like resistivity in terms of electricity. Exactly analogous. Any other questions? So in electricity, you would talk about the current density. The current per unit area is proportional to the voltage gradient, which is the voltage per unit distance. And that's, the ratio of those two is the so-called resistivity, as opposed to the resistance, which is what you get by scaling those by length and height. And it's incredibly analogous to this. Okay, just out of curiosity, let's do a new vote here. How many people got it right, got the quiz right? How many people got the quiz wrong? Private vote. I'm not doing raise hands, so you can just be honest here. Okay. Now, how'd we do here? Most of you got it right. Very good. Of those who got it right, how many think they would get it right if you were asked it at a random time in July next summer? Like, did you actually learn it? Okay, so next is not just to learn things, but to put it in a deeper filing cabinet where you can try to get access to it. Now, how can you do that is think about it. Think about it when you go to bed at night. Think about it when you're walking from one place to another, in the shower, on the toilet, whatever. Think about it. Okay, now I want to go on and talk about bending. And we had these popsicle sticks. Everybody take out your popsicle stick, your coffee stirrer. One for every pair of people this time. Now, I paid for these coffee sticks, so you're just throwing away my valuable money. It cost, the price of these sticks was 3 crackers. That's the Duffield coffee shop. They said, they had to call the manager and they said, charge him for 3 crackers. Okay, so now we take these popsicle sticks and we do this experiment where you push down with your chin. Half of you have done this in the lab, where you took various coffee stirrers and you pushed down with your chin and you actually measured the forces and the deflection with various fancy pieces of equipment. And what you find with this stirrer and with structures in general is that when you have long, narrow things and you try to bend them, they're a lot less stiff. They're a lot more compliant than when you try to stretch them. But somehow it's still the same thing. It's still that the harder you push, the bigger the deflection, or the bigger the deflection, the harder you push. But the scaling comes out different when you bend it than when you stretch it. Not only is it quantitatively different in magnitude, somehow there's a different scaling with length, width, and height. Now, I could try to get you to derive the formula here like I did last time with tension, but there's 2 things about it. One is that it's hard, so it would be harder for you to get the right answer. And the other is that half of you have just been given the answer in the lab already. So I'm not going to make a game out of trying to cook up a formula that half of you know because you did it in the lab. But I'm going to try and convince you of this bending, this weird formula for the bending stiffness. Try to convince you that it's sort of reasonable. So first of all, let's see. Got to start with clean hands here. Okay, so first of all, you think about starting with a clean slate. So you pick up the Purell, and you notice that the Purell has bubbles in it. And so when I washed my hands and squeezed this bottle, I saw these bubbles move a little bit. Now, usually you just see this clear liquid and you squirt it and something comes out. But what these bubbles allow you to do is something which you want to try to train your mind to do, basically from this point forward in your life, is that whenever you have a liquid or a solid and it moves, all of the atoms inside also move. And they move maybe together, but they also move maybe not together in a way where there's some distortion. And so here there are these markers, which are these bubbles. Who cannot see these bubbles? Okay, I'll pass it back and you can wash your hands. You can, but you see these bubbles and you squeeze this and you squeeze it in the top and the top ones go and the bottom ones don't. Whenever you take a solid or a liquid and you change its shape somehow, that corresponds to all the distances between all pairs of atoms inside changing, and you want to develop a cartoon for that. Thinking of inside the atom, you can label, inside the material, you can label various atoms. I'm just saying atoms, bubbles, whatever, markers, and you can think about that distortion. And that's the way we want to come to understand the bending, is by getting inside that coffee stirrer, that teeny little space, and trying to think about little atoms and little things stretching this way and that. Okay, so those of you in the back, you want to see this? You want to play with it yourself, or there you go. Okay, so take this stick here, and what they call this simple bending experiment is you hold it up like this. To make it so-called statically determinate, you imagine there are rollers over here, which means that you don't have to worry about it stretching. And you put some load over here like this, and you see that there's some force on this. Let me call it P, or it could be whatever we want to call it. This thing, if we draw a free body diagram of the whole structure, turns into something like this, with a P here, and a P over 2 here, and a P over 2 here. And we're trying to figure out how much this thing bends. Now, the nature of this bending is that it sort of curves all along the length somehow. Now, how can it possibly change into this shape? Is we want to get inside this little thin thing. Thin as it is, what did we figure out? It was 30 thousandths of an inch, which is, I know, about a millimeter or something like that. A millimeter is a thousandth of a meter, but atoms are on the order of angstroms, 10 to the minus 10 meters. There's still room for 10 million atoms up and down the length here. So small as it is, there's room for lots of stuff and deformation. There's room to zoom in here and see lots of deformation and structure. And even though you don't have a microscope, you want to zoom in your mind. So you get inside that popsicle stick and you think, well, if I zoomed in and it would look something like this. And as this thing distorts, it bends like this. And how can it possibly bend if there aren't little bubbles in this thing, just like there are bubbles in that Purell bottle, little atoms we could look at whose distances are changing. So in particular, if you just put a dot right here and a dot right here, when I push this like this, those two dots have to get closer together. Or at least relative to these two dots, they have to get farther apart. Or at least this has to get farther apart, or this has to get closer together, or both. This has to get closer together, or this has to get farther apart, or both. So that means when we get inside this wood, we can now think of it being made of fibers, and each of those fibers is just like this whole experiment was to start with. So we take this whole tension experiment, then we're going to go sideways and bend it, then we're going to look inside there and say this wood is made of teeny fibers. It doesn't have to be made of fibers. You can think of it in a continuum way, but it's easier maybe if you think of it as made of fibers. And each of those fibers is in a tension experiment. So when I bend this, there are all these fibers here that are compressing and here that are in tension. And each of those is obeying this rule that we got for tension, which is that this is getting shorter and this is getting longer in accordance to the fatness of the fiber and the length of the fiber by the formula we showed there. Now, the nature of this bending is that we have this whole collection of tension and compression experiments in here, and we have a whole collection of it here and a whole collection of it here. But to start with, let's just look at one little section here and look at this bending experiment. So a way of conceptualizing this thing is to draw a free body diagram, say, of just the right part of this thing, which has this thing going up here. I've cut this away, so I draw it only with a dotted line. and there's little forces here, but I'm just drawing with dotted lines. And when I cut this, I have to fool it. This is this idea of a free body diagram. And to keep this from flying away in space, there has to be some downwards force. And the standard engineering convention for that force is called V. I'm actually violating the sign convention of that, but that's not going to matter here. There could be a tension force, but it turns out to be 0. Otherwise, this thing will be flying to the right. And then there has to be some couple here, because there's a moment. This is trying to twist this. So when I look at this popsicle stick being bent this way, and then just imagine this right-hand part of it by cutting it like that, I have to fool it into thinking it's not cut. How do I fool it? I have to hold it down. That's that force V, and I have to apply a couple like this. Now, how do I go about applying that couple? Is I blow up that picture even more in my mind, and then in pictures. And when you blow up that thing even more in your mind or in pictures, we see we've cut this edge of the popsicle stick, and this is now going off like this. And there's some distribution of forces here, which are pushing down to keep the thing from flying up. And then what's applying that couple is there's a compression forces up here, and there's tension forces down here pulling on these fibers. So the fibers at the bottom are being pulled on, the fibers at the top are being pushed on. If we like, we could pull out some little fiber here and just look at that fiber and see that's a fiber which is in compression. And we could pull out some little fiber here and draw a free body diagram of that fiber and see a fiber in tension. Okay. Now, given that, how do we get the scaling of how much deformation we get and how it depends on the width and the height and so on? So what we'd like to figure out is in this experiment, we've got this P. We're going to get some little deflection here, which I'm going to call delta. That was analogous to this delta, by the way, Greek letter delta. It's analogous to what we call delta L for the thinking of a spring and tension. Now we have a spring and bending. And we're trying to find the relationship between this P and this delta and this L. And then the cross section of this, it has some width and some height. So what we'd like to find out is what is delta as some function of the length, the width, the height. And now I'll jump ahead and know that we know that the important material property is the Young's modulus. It's how much each of the intrinsic stiffness of the fibers. We'd like to figure out what that formula is. And we'd like to figure it out based on this cartoon that we have so far. Ready for me? Ready? All ready? Raise your hand. Questions before I go ahead? Okay, so now this is the reasoning that I'm not giving you as a in-class exercise. If I did, I would have to give you 45 minutes or an hour to do it. And as I said, it's not fair because you've seen the formula, some of you, already in the lab. But what do we know? Oh, by the way, there's got to be a P here, right? The applied load. We know that we're assuming that there's a proportionality. That the bigger the load, the bigger the deflection. That's the linearity assumption. Now, if I did 2 experiments like this with 2 coffee stirrers, okay, we're going to do short experiments. I have 2 coffee stirrers which are short. If I know the deflection of one when I apply a P, then I know the deflection of the other when I apply P. And I know that if I apply half the load, this deflects half as much. If I put 2 of them side by side and apply half the load to each of them, I get half the deflection I got originally. But since I applied half the load to each of them, it's the same as the same total load. Now they're side by side. I glue them to each other side by side. Nothing changes. So when I put 2 side by side, the deflection is half as big. So I know that when I put 2 by side is half as big. Now, I already know that I've got this material property, this intrinsic stiffness of the material. So I know that the stiffer the material is, the less the deflection is I'm going to get. So I know that I have an E down here. So now what I'm left with is some function, I'll call it F1 of L and H. And that part is the hard part. How does the stiffness of this depend on the length? How does the stiffness depend on the height? Well, now we can use dimensional analysis. This has dimensions of length. This has dimensions of force. This has dimensions of force divided by area. This has dimensions of length. Here I have a force divided by area and a force. So the units of the ratio of these two is an area, which is divided by length. So the units of this whole thing is length. So the units of this are equal to length. But the units of this are also equal to length. So that means the units of this are not length. But how can the units of this be not length? Any sensible formula that is anything but a power law has to have these be dimensionless. Otherwise, the answer would depend on whether I did it in SI units or English units. So it has to be, then, that the dependence on the length and the height has to be of the form of a function of the ratio of the length to the height, something dimensionless. All interesting functions have to be of dimensionless variables. Otherwise, they have the log problem that I mentioned last time. They'll depend on the unit system. So now we're left figuring out how does this thing depend on either the length or the height. If we can figure out either one, we know the other one. So what we're going to try to do is figure out how the overall compliance of this thing depends on this height. Okay, now I'm going to do this a little bit quickly. If I want to do it very carefully, I have to do a whole lecture on it. And that whole lecture you will get when you take Theoretical and Applied Mechanics 2020. And that whole lecture goes under what's called beam theory, or elementary beam theory, or Euler-Bernoulli beam theory. And I'm going to try to give you the basic result from that lecture, just with a hand-waving thing. So if you ask me to be too careful, it will take me 45 minutes. So you have to just follow the rough scaling here. And the rough scaling goes like this. What's happened in this little section here is we're doing this whole stack of tension and compression experiments on these fibers. And the question is how much do those fibers resist the overall bending of this overall beam? So here we have these fibers, and how much do they resist this? Well, if a fiber is farther from the center, it has a bigger lever arm resisting this rotation. So that means the bigger H is, the bigger each fiber's contribution is to this resistance to rotation, because it has a bigger lever arm in terms of measuring the moment of this force relative to this point. So that means we get a proportionality of H. But the bigger H is, the more fibers we have. So that means we have a proportionality factor of H squared. But the bigger H is, the more each fiber is stretched. Because when this squeezes like this, the middle ones don't stretch much, and the top ones stretch and shrink a lot. So for a given curvature of this beam, we get more stretch in the fibers if H is bigger. So we have three effects which make this thing stiffer if it's thicker. There are more fibers, proportionality H. They have a bigger lever arm, another proportionality H. And each fiber stretches more, another proportionality of H. So that means the stiffness, the resistance to bending of this, goes as H cubed. But that's the resistance to bending. So So that tells us that this has to be some constant times p divided by the width divided by e divided by h cubed. And now we know the dependence on h. That tells us the dependence on L, which is an L cubed. Now we could try to argue the L dependence also. That's actually a harder argument to make independently, but the dimensional analysis lets us figure it out directly. What does that tell us? This is something which is good to remember. One thing is that reasoning is maybe somewhat good to remember, but there's more important things to remember as an engineer, is that when you have long, narrow things and they're in bending, they get much more compliant when they're longer. If you take your popsicle stick and look at a short segment of it as kind of stiff, if you look at one that's twice as long, it's 8 times as compliant. Which is why, for example, the swimming pool diving board, you just change the support point a little bit, and it changes the compliance of the board a lot, because the compliance increases with the cube of the length. The compliance goes with the cube of the length. Similarly, the stiffness goes up with the cube of the thickness. If you have a thicker piece of wood, it's twice as thick. It's 8 times as stiff. 8 times as stiff. Huge dependence on stiffness. If you have square pieces and you have one square piece with twice the dimensions of the other, it's got 4 times the area, but it's got 2, 4, 8, 16 times the stiffness. Because the height went up by a factor of 2, and we get a 2 cubed, and the width went up by a factor of cubed. So the bending stiffness increases hugely with the thickness of the material in the bending direction. That's the intuitive thing you want to remember. There's huge dependence on thickness, which is why, for example, when you take a popsicle stick like this and you turn it on edge and you try to bend it, it's very stiff. How much stiffer is it bending this way than bending this way? Almost you can't see the bending this direction. How much stiffer is it? Well, we got the dimensions were 5 times as big in this dimension than this one. We measured it 0.150 inches and 0.030 inches. So we get 125 times stiffer that direction. Oh, oops, it's 5 times narrower. It's only 25 times stiffer. That's a lot. 25 times stiffer bending this way than bending sideways. Now, just so those of you who are curious about this machine I brought in, you can try to picture these things. Remember, I said you want to get inside that pure L and think anything you deform is a pure L. There's dots in there, you can keep track of it. And there are techniques to try to keep track of it, strain gauges and so on. There's an optical technique. So here's a little thing I can bend a little bit. And it turns out that this material is one that has these special optical properties that when you bend it, it changes the optical properties. And you can see this bending. Now, what do those lines mean? Here I'm bending this thing this way. I'm bending it, make it horizontal like this. I'm bending it. Do it some way you can see it. I bend it and you get all those lines. What do those lines mean? Those are lines of constant tension. So in terms of those of you who are taking Math 192, those are contour lines of the tension in the material as a function of position. The middle line is a line where the tension is 0. The lines at the top are where the tension are high. The lines at the bottom tension low. And these are more or less, the lines of constant tension are more or less parallel to this beam, the way I'm loading it here with 2 couples at the end. If you load it a different way with a point in the middle, then those lines do not stay parallel, and you get this funny distribution of deformation. So it's not quite so easy to understand what these contour lines mean in terms of deformation compared to the pure L. But what they do is at least give you a cartoon that even though I'm just distorting this a teensy bit, I'll show you how much I'm distorting this. So I'm going to distort this in this graphic this much, and you see those funny contour lines. The experiment I'm doing is this. You can't even see it, yet enough is going on inside that material to cause that so-called photoelastic effect, which means you can always think when you apply loads to material, even if you can't see it distorting, there is this distortion. There are these bubbles moving, there is this distance between the atoms, there are these fibers stretching, and even though all of that stretch is extremely small, you think I can exaggerate it in my mind, and it is going on, and I can think rationally about it and how it's distributed in space and so on. Okay, any quick questions about that? you see these? You see any weird curves or colors here? Do you see any words or curves, colors here? That's what the box is for. What is it? What is it? This is a circularly polarized filter. This is a circularly polarized filter. The distortion causes a change in the polarization of the light coming through here, which shows itself by going through these two filters. Okay? Yes? What C is a number which I couldn't figure out. In this particular loading, in this particular thing, I think it's 1 over 12. Then we have to get into the details to figure out. Then you have to take 202. If I wanted to figure out that number right here in front of you, first of all, you wouldn't understand what I was doing, and second of all, it would take me 20 minutes to figure it out.
What are the 3 factors of H?
So here you get that teensy deformation, absolutely teensy, 1 part in 1,000, but because of the geometry of this, it becomes visible because of this multiplication along the length. And that's what your lab's about today. Let's do 1 minute of questions and then end class. So this is a trick. To see it, it's like, hey, you said there's a trick. That's not a trick. That's dumb. But it is a trick, really, because when you do this deformation, something has to stretch and so on in the material. Just wait a second. Quick questions. Class too fast today? Raise your hand. Too slow today? So interesting that you can't stand it. Please be more boring. I just can't take it anymore. Okay. If you have any questions, comments about class, you can give them to me. You won't be punished in your grade if they're negative.